Second speaker is Masafumi Oizumi from the University of Tokyo. And his talk title is Introduction to Information Geometry. Okay, please.
Okay, thank you for the introduction. So I'm Masafumi Oizumi from the University of Tokyo. So today I'll talk about information geometry in the community of stochastic thermodynamics. So first, let me state the policy of this tutorial. I do not assume any prior knowledge on information geometry and differential geometry as well. So I only focus on the basics of information geometry, such as dually flat structure. And I'll prioritize intuitive understanding rather than accurate understanding. So the mathematical details will be omitted largely. So this is the overview of my tutorial talk. By the way, I shared my slides in the chat box. So please refer to that. So here is the overview. First, I'll very briefly introduce the what's information geometry, and I'll quickly introduce differential geometry, and I'll cover the basics of information geometry, and I'll cover the most important concept of information geometry, which is a dually flat structure, and finally I'll introduce some of applications of information geometry in stochastic thermodynamics. Okay. So I'll take questions at the end of each part, but you can interrupt me if you like anytime. So information geometry is a field of mathematics that aims to elucidate the geometry of the space of probability distributions. And the information geometry has been mainly developed by Shunichi Amari, who is actually my mentor when I was a postdoc. I used to be postdoc in his lab. And this information geometry has been applied to diverse research fields, including machine learning, signal processing, neuroscience, and physics, where probability distribution matters. So any field where probability distribution matters, I think that information geometry can be applied and useful. And as I said, that actually I'm not a physicist and I'm not a specialist of stochastic thermodynamics. That I'm a theoretical neuroscientist, and I worked with Shunichi Amari on the some mathematical problem in computational neuroscience field, and I utilize the information geometry for that purpose. But later, I worked with Sosuke Ito, who has been very actively using the information geometry for stochastic thermodynamics. And I and Shunichi Amari worked with him. And for example, that this is our work. And in this work, entropy production can be geometrically interpreted as sort of orthogonal projection in the Riemannian space of probability distribution. So I'll explain this in the later part. So that's why that I came to know the stochastic thermodynamics, and probably this is the reason why I was invited to give the tutorial in this workshop. So first of all, so what is information geometry? In information geometry, we consider the space of probability distribution. The simplest example is, for example, the normal distribution. So normal distribution is parameterized by two parameters, mean mu and variance sigma square. And we can show the space of probability distribution in this case in two. Sorry. Yeah. So these are two-dimensional space parameterized by mu and sigma squared. And each point in this space represents some particular probability distribution with these particular parameters. And these mu and the sigma square are the coordinates of this space. And the information geometry aims to elucidate the geometry of the space of probability distributions. And this asks questions something like, is it flat like a Euclidean space, or is it curved? Or how much it is curved? And also what are the natural coordinate systems to describe this probability space? And why information geometry is useful? So, why is understanding the geometry useful? It will provide us unified understanding of some existing different quantities or algorithms, or it can even lead to some novel quantity or algorithms from the viewpoint of information geometry. For example, that some novel quantities can be derived by the decomposition of KL divergence, or some novel algorithm is, for example, natural gradient. That is probably the most famous example that is derived from the information geometry. So how can we analyze this geometry? Actually, the differential geometry is necessary for analyzing the geometry of the space of probability distributions. So I need to introduce differential geometry very quickly in the next part. Okay. Yeah. Okay, let me move on to the next part. So this is a extremely quick introduction of differential geometry. So in the differential geometry, we analyze so-called manifold, which is a locally Euclidean space, but has a different global topology. For example, the surface of a sphere. Surface of a sphere, locally, it is like a Euclidean space, but globally, this is not. It is curved, and yeah, and it has a totally different topology. And to describe this manifold, we introduce coordinates, xi. And at each point, we draw some tangent space. We consider the tangent space at each point on the manifold. And then again, that this tangent space can be considered as a usual Euclidean space. So you can do a basic linear algebra of the vectors. And we consider the tangent vectors in this tangent space, which are considered as basis vectors in this tangent space. And with this, what determines the geometric property of the manifold? There are two things. One is metric, which is sort of inner products, which can be computed by an inner product of the basis vectors of each tangent space. So this metric determines the local distance, meaning this local distance can be different at each point of the manifold. So the xi is here. And if this metric is positive definite, it is called the Riemannian metric. And in information geometry, we consider a Riemannian metric, meaning that the Gij is a positive definite matrix. And the second one is connection. And we consider the tangent space of the manifold, and these tangent spaces are totally different at each point, and we need some connections for smoothly connecting the different tangent spaces. And this connection is given some kind of a sort of linear transformation. And in that case, that we call this type of connection affine connection. So given these two things, we basically know that whether the manifold is curved and how much it is curved. But let me explain the two components a little bit in more details. So first about the Riemannian matrix. Again, that coordinates of the manifold is given xi, and we have tangent vectors of the tangent space n tangent vectors, and the Riemannian matrix is given by the inner product of tangent vectors, and we assume this positive definite matrix. And the distance between the point P and P prime in the same tangent space is given by just in the product of dxi. And this can be computed as dxi dxij times the inner product. And it is expressed as dxi dxij dij. By the way, so we used sort of Einstein rule where that we omit the summation ij if same index appears in the upper index and in the lower index. Okay, so again that the distance in each tangent space can be determined by is determined by Riemannian matrix. So that's why I say that this Riemannian matrix is local distance measure. Or you can think of this as some kind of ruler of each tangent space. Okay. Then, but a difficult thing is that again that the tangent space are totally different or really different. I mean, if it's far apart. But if you consider the nearby tangent spaces, it is similar, but of course different. So how different the tangent space can be expressed by this affine connection. And but a difficult thing is that again the basis vectors are different, and also these things belong to different spaces. So if you express the tangent vector at xi plus dxi by tangent vector at xi, you can first the component vector which exists, which lies in the tangent space at xi, but you have also some vector component which does not belong to tangent space at xi. But in differential geometry, we basically do not care or cannot care about this component. So we basically do not consider this, and only considers this term. Okay, and the difference between the tangent vectors between the nearby tangent spaces are expressed by this, and this is called the covariant derivative. And this difference is expressed by this gamma term, which is called affine connection. Okay, so this is a sort of definition of covariant derivative, and this quantifies that how much the two tangent vectors are different. Okay. Then here is a specific example of the affine connection and the Riemannian metric. This is easy example where we can explicitly compute everything like by a simple algebra. So in this case, this is just 2D surface of a 3D sphere. So we have the coordinates of the manifold like this. And as you can see, this is sort of polar coordinate, and we have only two independent coordinates, theta and phi. So this is a two-dimensional manifold. And tangent vector is just simply computed by the derivative of p, vector p, like this. And this is something like this. And also the tangent vector E2 is computed by a derivative of p with respect to phi, something like this. And then given these, tangent vectors, Riemannian metric is given by this. In this case, just identity matrix. So because these are the orthogonal vectors. Then affine connection is also simply computed by some differentiation, and the difference given by like this. So the vector E1 is differed by this amount. But again, that E3 is, by the way, the orthogonal vector with respect to the surface. So this term we don't care. So we omit this, and we only consider the this term. And this minus sine theta or sine theta is affine connection in this case. So again, that when we consider manifold embedded in the Euclidean space, we can simply compute the metric and the connection by differentiation. But in more general case, we consider the case where we basically do not know what kind of space the manifold is embedded in. And only the metric and the connection of the manifold are given. That's the situation we are dealing with. So again, that the Riemannian metric and the affine connection. And interestingly, only with this metric and the connection, we can know whether the manifold is curved and the curvature of the manifold. That's sort of surprising or theorem proved by Gauss. And the next one. So to summarize these sort of intuitive understanding of differential geometry, so by analogy, it's like patchwork. Like as I said, that we consider the tangent space at each point in the manifold, and we connect these tangent spaces to understand the whole geometry, entire geometry of the manifold. But you need to be careful about that, the fact that the two nearby spaces are totally different. Like this space and this space are different in terms of the metric. And also the tangent vectors are different. So you need to connect these tangent vectors with affine connection. Okay. So far so clear. So I'll give you two more important concepts to finish before we finish this part. So first one is parallel transport. So this is just a generalization of parallel transport in Euclidean space. So consider some vector field A along curve Xi, connecting the P and Q. So we consider some vector field, and then the covariant derivative of A along the curve is computed as something like this. So again, we use this affine connection thing here, and we can compute this the covariant derivative with respect to t is like this. And the parallel transport of A along the curve is defined as covariant derivative being 0, meaning that with this the component of A, basically the direction of component A does not change, basically. And this is the equation for the parallel transport of vector A. And by using the concept of parallel transport, we can define the geodesic, which is an analog of a straight line in Euclidean space. And in this case, we consider the tangent vector of curve itself, Xi, and this is just the derivative of Xi with respect to t, so Xi dot t. And when the covariant derivative of the tangent vector of curve Xi dot t along itself does not change, the curve is said to be a geodesic. So this direction, if this direction does not change, then it is geodesic. So this condition is also can be simply obtained by the parallel transport equation, like that we can consider Guzai.t as a vector field, and we put Guzai.t into this AT, then we get the equation of geodesic, which is complicated. And geodesic is a natural extension of a straight line in Euclidean space again. Then the final thing is that Levi-Civita connection. So we, in the general case, we could consider the metric and the connection separately. But the question is there some natural way to determine the connection from the metric? Is there any relationship between the connection and the metric? A standard way to determine the connection is imposing the following two equivalent conditions. First one is inner product of two vectors does not change by parallel transportation. Inner product AB and inner product of parallel transport of A and B. And equivalently, the second condition is a curve that connects 2 points by a minimal distance is a geodesic. This seems natural, and it has been used in mathematics and also in physics. And this condition gives us a so-called Levi-Civita connection or Riemannian connection, which is given by this. So this, again, that the affine connection is given by some derivative of Riemannian method. Okay, that's a very quick introduction of differential geometry. So do you have any question? Okay. Then I'll explain the basics of information geometry. So by the way, so if I state sort of final conclusion, actually that in information geometry, we only consider flat structure. So although I already introduced some complicated things, but I mean, at the final part, we can simplify these affine connections, things like that. So anyway, so back to the space of probability distribution or normal distribution. Again, that we consider the very simple example here. This space is parameterized by mean and variance sigma squared. And the question is, what is the metric and the connection in the manifold of probability distributions? You can choose whatever you like in principle, but is there any reasonable choice for the metric and the connection? Information geometry answers yes to this question. So how can we choose some reasonable measure? So first, about the metric in the space of probability distributions. So let's consider these 4 points A, B, C, D. And if simple Euclidean distance is used, for example, distance AB and CD is the same, but the probability distributions look like this. Like probability distribution A is like this, and B is like this, and A and B are overlapped pretty much. On the other hand, that probability distribution C is like this, D is like this, then overlap is very smaller than the AB. So in this sense, these distances cannot be same, right? So a different metric of distance is necessary to get a reasonable results. So the natural candidate of the distance measure is Fisher information. And this Fisher information is characterized by the Cramer-Rao bound. So the definition of Fisher information matrix is given by like this, like the derivative of log p, I mean derivative with respect to the parameters of probability distributions. And this is the expectation with respect to p. And the Fisher information matrix is positive definite. And interestingly, this Fisher information matrix determines actually lower bound of variance of any unbiased estimator of the parameter xi. So this Fisher information matrix determines the accuracy of the estimate. So closely related to estimation theory. And Rao discussed the Rao actually proved this, Cramer-Rao bound. And Rao already discussed the idea of regarding Fisher information as a Riemannian metric in his 1945 monumental paper, and this can be considered as the origin of information geometry. So again, that to capture the Cramer-Rao bound, that again the larger the Fisher information is, the smaller the variance of the estimate is. So the larger Fisher information means that the distance between the probability distributions around that point is large, meaning it is separable, right? So we can use Fisher information is a metric of some local distance. But note that Fisher information matrix only gives a local distance between two nearby points, but it does not give us any information about global distance between two far away points, and how tangent spaces should be connected. So we need something else. Is there any reasonable distance measures between two probability distributions? So you probably know something, which is Karlbach-Leibler divergence. And Karlbach-Leibler divergence is not distance, but because this is not symmetric, so it is called divergence. And this Karlbach-Leibler divergence that is characterized by so-called Sanoff theorem. So this theorem is something like when we get n samples from the probability distribution p, the probability where the estimator of p is equal to q is given by like this. So if the KL divergence between P and Q is large, then this probability decreases exponentially. So this KL divergence can be considered as some measure of separation between P and Q. And interestingly, if you exchange the role of P and Q, like true distribution is Q and the estimator is P, naturally this gives us a different quantity. So the KL divergence is asymmetric by nature. And we can expect this KL divergence may provide us the information about metric and also a connection. And actually it is. So first, that the metric can be derived by the second derivative of the KL divergence. So consider the KL divergence between the some cross points xi and xi prime, and we can expand the KL divergence between these things around xi prime equal xi, and then by usual Taylor expansion, we can see that this first term disappears and only the second term remains. And this second term turns out to be Fisher information matrix. So Fisher information metric can be derived from the second derivative of Kerr divergence. And I need to omit the proof, but we can derive also the connections, affine connections from the third derivative of the Kerr divergence. And actually, that in this case, we can derive two affine connections, which called dual affine connections, because of the asymmetry of Kerr divergence. Like this second derivative is shown here. So this case that these are derivative applied to the left one, and also the in this dual connection, the two derivative is applied to the right one. So that gives us two different affine connections. And this affine connection has some very nice property, meaning that these dual affine connections are related to a Levi-Civita connection, gamma 0, in this way. Again, that I totally omit some mathematical proof, so you need to believe me, but things like that. So this dual affine connections is related by this, meaning that just half of the two dual affine connection is Levi-Civita connection. And also these dual affine connections is related by this so-called symmetric cubic tensor, which is simply expressed by the sort of the triple product of di log p. So that's sort of similar with Fisher information metric, right? But anyway, so this is pretty much complicated, but good news is, I mean, really complicated, but we can prove that manifolds with the above dual affine connections are both flat, meaning that the so-called Riemann-Christoffel tensor is 0, and in the same way that there exists a dual coordinate system theta and eta, where the affine connections, these affine connections are 0 at every point. And such coordinate systems are called affine coordinates. So we introduce very complicated things, but if you stick to this dual flat structure, then things gets much simpler. Like if we use dual affine coordinates, then we don't need to care about the connection things. It's like similar to Euclidean space. Of course, it's a bit different, but we can have some intuitive. We can use our intuition. But anyway, so what is the benefit of dually flat manifold? So dually flat manifold can be considered as some generalization of Euclidean space. And with affine coordinates theta or eta, the parallel transport looks complicated. Over vector gets simple, like gamma is 0, then parallel transport is simply AI is constant. You don't need to change AI. That's it. And similarly, the geodesic is just a linear form of the affine connection. So with gamma is 0, then theta, the equation is like this. So the geodesic is just a linear straight line. Very simple. And also, whether submanifold S is flat is simply judged in a dually flat manifold, because that S is flat when S is defined by some linear constraint of the affine coordinates, like this. So it is analogous to a plane in Euclidean space. So this is pretty much the very benefit of dually flat manifold. And in this dually flat manifold, we have very useful theorem, which is a generalized Pythagorean theorem. So it's like when the triangle PQR is orthogonal, such that the dual geodesic and also the geodesic is orthogonal, then the following generalized Pythagorean theorem holds. Like this is a Kerr divergence. Kerr divergence PR is equal to Kerr divergence PQ and QR. By the way, dual geodesic is that determined by dual affine connections, and also this is another the other affine connection. And as I said, geodesic is simply expressed by just a linear line in this way, but with respect to different coordinate. Then the orthogonal condition is just inner product of theta and error is 0 at this point. Then we have Pythagorean theorem with the Kerr divergence. And similarly, we have another useful theorem, projection theorem. It's like just a projection to the plane, to a plane. So consider the orthogonal projection from the point P to the submanifold S, and in this case we consider the flat submanifold, like plane in Euclidean space, and let the foot of the perpendicular line be Q star. Okay, this is a orthogonal projection. Then when S is flat submanifold, this Pythagorean theorem holds for any point Q in S. Like divergence PQ is equal to PQ star plus Q star Q. Thus the Q star is the point that minimizes the Kerr divergence between P and the submanifold S, right? Because that this is larger than this, because of the Kerr divergence is positive. So that's the projection theorem, like that if you do the orthogonal projection, then this is a minimized divergence. Okay. So this is very useful property of dually flat structure. So to summarize this part, so we construct information geometry starting from Kullback-Leibler divergence, and Kullback-Leibler divergence gives us Fisher information metric and also dual affine connections, and this connection gives us a dually flat structure. And we know that the probability space is simply flat manifold. But we are also interested in what if what if we use different divergence other than Kerr divergence? Like we can start from other divergence measure, then we actually can derive the metric and also dual affine connections in the same way as we did in the Kerr divergence. So we can have more general metric and affine connections, and we can ask what kind of structure this is, right? And Amari actually sort of investigated this issue. And but if we do not restrict ourselves about the choice of general divergence, it is sort of too difficult. So we require something which is invariance and decomposability. Invariance is that depending on the coordinate choice, the geometry should not change, something like that. But I skip the details. But if we require this invariance criterion and also the decomposability of divergence, the class of divergence is restricted to so-called F divergence. So F divergence is expressed by something like this. And the F divergence includes Hellinger distance and K divergence, alpha divergence, etc. And we can, again, derive the metric from F divergence. But interestingly, even if we consider the general F divergence, what we get as a metric is always Fisher information metric. And so Fisher information metric is very sort of unique metric, right? I mean, just with the invariance criterion, we always end up with Fisher information metric. And then we also get dual affine connections, gamma star, right? And what about the geometry? Actually, the geometry is not flat in general, but only when that K divergence is used, the manifold is dually flat. So K divergence is unique measure, unique divergence measure that is flat and decomposable invariant. So if we want to consider the very clean geometric structure of probability distributions, I mean, K divergence is a way to go. That's the end of the third part. I'll move on to the next part, so which is a dually flat structure. So let me give you the specific example of dually flat structure, which is given by exponential family distribution. The exponential family distribution is expressed by this, and then introducing some notation here. Then we can rewrite the exponential family distribution as like this. This is some standard form of exponential family distribution. And here theta is a parameter and x is a random variable. And then the example of exponential family distribution is first that the normal distribution is example. And here you can see that x1 is x, x2 x squared, theta1 is there, theta2 is there, something like that. And also the second important example is discrete probability distribution is exponential family probability distribution. I mean, any discrete probability distribution. Like we have n discrete states, and we have probability for each state. And then the distribution is expressed by like this, by this. And we use some delta function. And we can rewrite this as exponential family distribution form. And here the parameters is, for example, expressed like this. So these are the very important examples of exponential family distribution. And then let's look at the how the dually flat structure is expressed in this exponential family distribution. So to go forward, I'll explain about some useful theorems to express effectively express exponential family distributions. So first one is that in dually flat manifold, there exist two convex functions, phi and psi and phi, and that are related to two affine coordinates theta and eta by Legendre transformation, like this. By the way, this is general theorems that hold in the general dually flat manifold. So that does not restrict to the, limited to the probability distributions. And also another theorem is in dually flat manifold, canonical divergence between P and Q is uniquely determined, which is given by these, convex functions and dual affine coordinates. So we are going to use these theorems. So what are these convex functions and affine connections and the canonical, affine coordinates and the canonical divergence in exponential family distribution? So again, that exponential family distribution is expressed by this, and dual convex functions are actually, in this case, first one is free energy. So some sort of normalization term in the probability distribution. And this free energy is a convex function with respect to theta. So theta is one affine coordinate system. And also another, dual convex function is entropy. And this is a convex function with respect to eta. And the eta is the other affine coordinate. And the eta is actually can be computed by the, the derivative of psi with respect to theta. And it turns out to be the expectation of xi. So we have now the dual affine coordinates, meaning that the theta is one of them, and also the expectation of xi is the other one. And the canonical divergence is given by this, and you can compute this as Karlbach-Leibler divergence. So we have everything for the exponential family distribution, affine coordinates and the divergence and convex functions. Okay, and as I said that this is a flat manifold. So that's the end of first part. Is there any question? Okay, then I'll move on to the final part, applications. So I'll show you some applications using the projection theorem, and also some lengths measured by Fisher information metric in the probability space. So first one is that Sosketo's and work, and also me and Amari collaborated with him. And in this work, we use a projection theorem to geometrically interpret entropy production. So in this case, we consider just a state transition from time t and time t plus dt, and joint probability. We consider joint probability distribution, something like this, and t is transition probability. And we to derive the entropy production, we consider some so-called backward manifold. This backward manifold is some sub-manifold in the entire space, because that we restrict this distribution like this, meaning that the conditional probability is same as sort of true one, but you can freely choose the marginal distribution over z prime, I mean the state at time t plus dt. So the freedom is here, but this conditional probability distribution is restricted. So this manifold is, again, that some manifold, sub-manifold in the entire space. And we can easily show this is a flat submanifold. So you can apply again, the projection theorem, and orthogonal projection is uniquely determined. And also this orthogonal projection always gives us the minimum of the KL divergence. And we can show that the entropy production is some minimized distance between the point P, joint probability distribution, and the backward manifold. So this is given by just a KL divergence between PS and the QS star. That's entropy production. So what's the benefit of sort of de-interpreting entropy production based on projection theorem? One of the reasons is I think that we can have some clear relationship between this total entropy production and also the partial entropy production. So this is so difficult to explain, but yeah, I'll try. So in this case, we consider the two variables x, y at time t, and also x prime and y prime at time t plus dt. And we consider the transition probability of only the subsystem x, like given y prime and z, what is the probability of x prime? And here we want to quantify the sort of the entropy production in subspace, subsystem X. And for this purpose, we consider the different manifold, the sort of local backward manifold, like this. So in this case, that we use the same sort of transition probability of subsystem X, but we can freely change. We can freely alter the distribution over y and z prime. And again, that the partial entropy production of subsystem X is some minimized divergence between the P and the local backward manifold. So this does. And here we can easily show that this partial entropy production is always smaller than the total entropy production, because that for deriving the total entropy production, we consider the sort of smaller manifold or submanifold, which is included in local backward manifold. So if you do the orthogonal projection in submanifold, then you always end up with a bigger distance, right? So the distance between this and that are always, this is larger. So the point is that from the projection theorem and the geometric interpretation, we can sort of very intuitively and graphically understand the relationship between the total entropy production and the partial entropy production. And in this paper, we also considered some special case where some interesting geometric theorem holds, but I'll skip that part. So the next one is that the importance of using the this length determined by Fisher information matrix. So the most sort of prominent example is so-called natural gradient. This is not related to stochastic thermodynamics, but I'll give you the explanation a little bit. So let's consider some regression problem or some machine learning problem where we try to find the optimal parameters of a probabilistic model that minimizes training loss. And training loss is, for example, given by some log likelihood over the data samples. And the simple way to optimize the parameter is just a simply steepest gradient descent, which is just derivative of L with respect to xi. So we sometimes are satisfied with this method, but this is not the steepest direction in the parameter space. As we saw, the length in the parameter space should be measured by Fisher information matrix. So in this case, if you go different direction, this distance is different, totally different, depending on directions. So even in Euclidean sense, you move same amount. In terms of this Riemannian metric sense, this distance are totally different. So you need to correct this difference by the Fisher information matrix. And the actual steepest descent in the parameter space is given by something like this. So we need to take the product of the inverse of Fisher information matrix. That's a very sort of effective correction of steepest descent method. And it is known that it works better than the usual steepest descent method. And this kind of the length in parameter space, it has some important meaning even in stochastic thermodynamics. So Crookes defined the so-called thermodynamic length, which was originated in this Wayne-Hold paper, as length of a curve on the Riemannian manifold of the thermodynamic space, like some trajectory from t equals 0 to t equals tau. We quantify the length, this trajectory in parameter space. Then this thermodynamic length actually bounds sort of the amount of dissipation. And but in this paper, he considers only the canonical distribution, meaning that the system at equilibrium. And in this case, that this distribution expressed by exponential family distribution, and affine coordinates is theta, and also the expectation of x. And x is, for example, that some potential or volume, and the theta is inverse of temperature, and also the beta pressure. And these are the dual affine coordinates. And the two dual convex functions, by the way, are free entropy and entropy. And these affine coordinates are related by Legendre transformation. That's the thing of introducing information geometry in the in the interpretation of thermodynamic length. But again, this is limited to equilibrium systems. But Sosuke Ito actually extended this result to non-equilibrium systems, and he considers general situations, and he starts from discrete probability distribution, and from the master equation he derives the expression of the thermodynamic length like this. So I'll skip the details, but the important point here is that Ito-san clarified the connection between information geometry quantity and thermodynamic quantities in general non-equilibrium systems. And he also derived the thermodynamic uncertainty relationship between speed and thermodynamic cost, which is topic of the next tutorial. But for the sake of time, I think I should skip the details. So let me summarize my tutorial. So information geometry characterizes the geometry of the manifold of probability distributions. And manifold of exponential family distributions has a dually flat structure whose metric is Fisher information, and divergence is scale divergence. And by utilizing the geometric properties of the manifold, we may be able to obtain a deeper understanding of various quantities in stochastic thermodynamics, and even yield the novel quantities or inequalities, I hope. Yeah, that's the end of my talk, and I finally would like to thank Dr. Shunichi Amari for for providing me knowledge of information geometry, and also Sosuke Ito for letting me know the stochastic thermodynamics. Yeah, thank you.